This comes out of section 5.4, the second derivative test. So in this question we're asked to find max, min, and points of inflection and use them to sketch this function y equals x to the fourth minus 8x cubed. So my first thought should be I need to find some derivatives. My first derivative, 4x cubed minus 24x squared. If I want to use those to find max, min, I better factor it as much as I can. So we have critical values at 0 and 6, and so I can check 0 and 6 to see what's going on there. I find if I put in a number to the left of 0 that I have decreasing between 0 and 6, still decreasing, so I don't have a min or a max at 0, but then after 6 it starts increasing, and so I do have a maximum at 6. Sorry, minimum at 6, a minimum at x equals 6, and we'll figure out what the y value is for that in a second. I'll find out the second derivative, and it'll be 12x squared minus 48x. Do a similar kind of work with it, factor it, and I get two numbers of importance here, 0 and 4. If I pick a number to the left of 0, negative 10, I'm going to have a negative times a negative, so I have concave up. Pick a number in between, like 2, and I'll have a positive times a negative, so concave down, and any number greater than 4 gives me concave up again. So I do have points of inflection. At x equals 0, and at x equals 4. So again, we do need to figure out some y values if we're actually going to sketch these, but we have enough information to do even just with this, because it's a polynomial without asymptotes, without any real major complications. We should actually be able to sketch this fairly well. If I want to go right up to the top and say, well, if I factored the original, took out an x cubed, I'd have x minus 8. So in drawing this, the reason why I do that is because it's useful to have the zeros. So at x equals 0, y equals 0, and at 1, 2, 3, 4, 5, 6, 7, 8, I have another intercept here. So 0, 0, and 8, 0 are useful points for me. The other information that I have is that at x equals 4, if you plug into the function, you get y equals negative 256. So my scale is going to have to be pretty big here, but 4, negative 256, somewhere way down here. I have a point, and that point is a point of inflection, where it's going to go from concave up to concave down. From concave down to concave up. And at 0, there's also a point of inflection, but I already have that point on my graph, that y equals 0 there. But at x equals 6, I can go back up here and put 6 into the original, and I get y is negative 432. So 6, negative 432, somewhere way down here, which does agree with the information that I've got so far. So if I start at the far left, I should be decreasing, and I should be concave up, and all the way until I get to 0. So I've got something like this. At 0, I continue decreasing, but my concavity changes, so I end up with concave down until I get to here. At 4, the concavity changes to concave up from now on, but I continue decreasing until I get to 6, and then I start increasing for the rest of the graph. And I have actually quite a nice picture of a 4th degree polynomial, in some ways better than what you'd get for your graphing calculator, because it has not just zeros and minimum on it, but it also has this point of inflection that would have been hard to trace to on a regular graphing calculator.